I'm here not to talk about that and meetup scheduling, but indeed about computer chips and how you can make them from your .NET software. Now, why I wanted to give you this talk is because as a .NET developer, you perhaps weren't aware that you can do some super cool stuff like this. Well, you do need that tool for that, Hastlayer, that I will show you. But still, as a .NET developer, you have some skill that otherwise a hardware engineer does. So let's see. But before going any further, a little bit of introduction here. I'm from a company called Lombiq Technologies. In our day-to-day activities, we are a .NET web development shop working mostly with the ASP.NET Core content management system called Orchard Core, and its previous edition, Orchard 1. That's where we are actually market leaders and the biggest team in the world, with clients like Microsoft itself, the Smithsonian Institution, or Live Nation. And actually, our very first client was NICE, the National Institute for Health and Care Excellence, which was quite a cool trip to Manchester. But when we are not doing Orchard development, then we are doing some research and development. And one of our R&D projects is Hastlayer, that I would like to show you. But before talking about Hastlayer, let's talk about you. So let's suppose that you are doing some number crunching in your application. And by number crunching, I mean some computationally heavy algorithms, like in the area of artificial intelligence, large language models like what we have seen with GPT-3, 3.5, 4, or other non-OpenAI algorithms included. Or you are doing something with images, so image or video processing, or downright computer vision. Or you do algorithmic trading on the stock market. When we are talking about the stock markets, not just every millisecond, but literally every nanosecond counts. It's mind-blowing. When we are talking about high-frequency trading, that's where you have to think about pretty much every clock cycle. Or your algorithm does something in the data compression or cryptocurrency sphere. Now, if you have such an algorithm and it's not fast enough, then you have a couple of steps to take. The usual ones that we as .NET developers do. First, you will check out, or you need to check out what's actually slow. So you profile your algorithm and try to optimize the slow parts. Let's suppose that you have already done that. Secondly, you parallelize it. So if it was a single-threaded algorithm, you can make it multi-threaded, not with threads directly, of course, but with an abstraction like the task parallel library, and, well, utilize more cores on a CPU. But let's suppose you have already done that as well. And lastly, you can use, of course, either faster hardware and or more hardware, so scale out or up, which in the cloud is, of course, very simple. Let's suppose you have already done that, or rather you have exhausted the feasible options here. So you can keep throwing money at the problem, but it doesn't bring enough benefits anymore. Or you don't have unlimited money to throw at the problem. Then you can take alternative approaches, where one of them is using heterogeneous computing. That means that you would utilize not just the CPU of a server or of a PC, but rather some kind of accelerator card like GPUs, video cards, or FPGAs. Now, let's talk about FPGAs, because you probably haven't heard or haven't used FPGAs that much before. An FPGA is a field programmable gate array. That means it's a chip that can, within limitations, of course, be dynamically reconfigured or rewired. So that means that you can make it behave like pretty much any other computer chip. Of course, it has a capacity, so this is within limitations. For example, if you want to accelerate physics of your computer game, you can configure an FPGA to do that. Or if you have your own compression algorithm, then you can also configure an FPGA to do that. Now, even if you haven't worked with FPGAs before directly, I'm pretty sure that you have used them in some way. For example, if you Google something on Bing, then you have used FPGAs because Bing is accelerated by FPGAs. I'm not sure about new Bing, so the large language model using one. Or if you have used pretty much anything from Azure, then you have used FPGAs too, because Azure uses FPGAs for networking. But sometimes FPGAs can be found in household appliances like routers, or less household appliances like X-ray machines, or even self-driving vehicles. Now, that's great, but one thing you have to understand when it comes to FPGAs is that it's not programming. You have to be a hardware engineer to create pretty much logic hardware for it. So just to alleviate some confusion, although I've shown you a picture of a chip when talking about FPGAs, and FPGAs also have visible circuit boards, that doesn't mean that they have anything to do with something like a Raspberry Pi that from a distance looks similar, because a Raspberry is pretty much a small computer. Similarly, Arduinos are something completely different, and Arduino is a microcontroller platform, so something completely else. Although, that being said, FPGAs are sometimes combined with these. I think I've read about somebody integrating an FPGA with a Raspberry just as with an Arduino, and at least there are various system on chips and microcontrollers combined with FPGAs. Now, why would you use FPGAs as a software developer? FPGAs are used in hardware development. So when you are designing a CPU, well, perhaps that's not something that most of us do. I personally haven't designed a CPU before. But when somebody is designing a CPU, then they use FPGAs for simulation. But we are not talking about that. We are talking about hardware acceleration. And to understand that a little bit better, let's compare different computing devices. So what they are good at. So let's talk about how CPUs and GPUs and FPGAs compare. And let's talk about parallelism first. So how many things you can compute at the same time. And a CPU can have something like 4, 8, 32, maybe 64 cores, but that's about it. So I would say that when it comes to parallelism, a CPU is on the lower end, or CPUs in general are on the lower end here. But GPUs are really highly parallel devices. I think they are on the other extreme here, because although the little processing cores on a GPU are much simpler than a CPU core, still it has thousands. And finally, FPGAs don't really have cores, but the level of parallelism you can get with an FPGA is roughly in the order of hundreds. So kind of in between. Now, what about the programs you can run on these devices? And when it's software, you can run it on a CPU. So CPUs win here. You can run anything on them. GPUs are again on the other extreme, but on the lower end, because with a GPU, the programming model is much more limited. A GPU is not a general purpose computing device, although there's something called general purpose GPU, but let's not go into that. Because GPUs are good with certain kind of computations. That's their goal. They don't have to be good with just any kind of computation like CPUs do. And FPGAs are, again, kind of in between. Now, lastly, power efficiency. And this is where FPGAs really shine. So CPUs and GPUs are, I think, on roughly the same level here, although this whole thing here is a totally non-scientific, just rough estimation to give you an idea. But FPGAs are really, really power efficient, because when you are executing an algorithm with an FPGA, then it just does what you need to be computed. There's no operating system to run. There's not even an instruction set like for a processor. You pretty much hardwire the logic into the hardware that you need. And of course, power efficiency is not just a goal in itself. Sometimes, like in the space industry is, but usually when we are talking about power usage, we are talking about costs. So to run the same algorithm, you can do it a lot cheaper with FPGAs because they use a lot less power, which means a lot less power draw to begin with, and secondly, a lot less power to cool them away. But there's a big downside. As mentioned, you have to be a hardware engineer to utilize FPGAs, because programming a CPU is easy enough. Programming GPUs, that's also possible for most developers, but utilizing an FPGA is something completely different. It's not programming. You are not programming a processor, but you are kind of creating a processor. So you have to think in terms of logic gates and wires and clock cycles. It's super low level. If you thought that assembly is low level, well, this is at least 2 levels lower, or even 3, because it's not CPU instructions, it's not machine code, it's not microcodes, it's just the bare metal. But with tools like Hastlayer, we intend to bring this complexity down to the software development level. So, speaking of which, what's Hastlayer actually? Hastlayer is a tool that takes a computer program and turns it into an equivalent FPGA logic. So, we could also say that it takes a computer program and turns it into a computer chip. That's kind of the tagline that you have already seen. Or we could also say that we kind of try to get the logic out of a piece of software, out of a piece of code, and try to create some equivalent logic in hardware, something that computes the same thing. And of course, we are at a .NET meetup, we are talking about .NET. And we are actually talking about .NET, not just something like C#. Because what Hastlayer processes are the .NET assemblies. It actually decompiles them. We didn't write the decompiler, we used the libraries of the decompiler ILSpy, which is a great tool in itself. But we use just the underlying libraries to kind of build a C# abstract syntax tree from any .NET DLL file, pretty much. So that means that you can use not just C# or Visual Basic, but also like C++ or function languages like F# or even scripting languages. Now, to get to the point why we are doing this is because with Hastlayer we can get the benefits of FPGA computing without learning about FPGAs. So first, you can get a very substantial performance increase due to the increased parallelism if your algorithm is highly parallelized and compute bound or memory bound even. Secondly, you can get a much higher power efficiency, so lower costs for the same computations. And also it's good for the environment, of course. And it's still software development as usual. You don't have to be a hardware engineer to actually get all of these benefits. So, a lot of talk until now. Let me show you how the whole thing actually works. So I'm switching over to Visual Studio, and what I'm showing you here is some sample code. By the way, everything that I show you here and also all the performance measurements that we have done are up on GitHub. Hastlayer and everything related to it is open source. So you can check out all the details on GitHub too. I will show you the link in a bit. And what we see here is something called a parallel algorithm. And you might not have guessed, but this is a highly parallel algorithm. And what it actually does is pretty much this. This is not a real-life example. This is kind of an exaggerated example of the kind of algorithms that are especially suited to be accelerated with FPGAs, with Hastlayer. So as you can see, this is just some simulation of a number crunching algorithm. So we have some conditional logic here, which is executed 10 million times. And what's important here is that the whole thing is done in a parallelized way. We are starting this logic in a new task. Now, if you're not that familiar with tasks, I'm using the taskbar library of .NET here. For now, you can think of them as threads, but tasks are not actually threads. They are much smarter. When you start a task here, eventually it will be executed on a thread, but .NET makes sure that all of this happens in an efficient way. So we are not oversaturating the CPU. We are not starting too many threads. And this is especially important because we start this many threads, and this many is 260. So we run this kind of simulated number crunching algorithm here on 260 threads eventually, but with a level of parallelism of 260. What this means that if there's a 4-core CPU, then still those 4 cores will execute these tasks with a hardware level parallelism of 4. So more than 4 won't actually execute really in the same time. But .NET will make sure that those 4 cores are fully utilized. What's more interesting, though, is what happens when we turn this into a piece of hardware. Then we will actually have 260 cores generated for us. On the hardware, this will be turned into kind of a processor just for us, that has 260 cores that only do this code here. So that's where the benefits come from. By the way, the rest of this class here is just some plumbing, so like waiting for all of these tasks and creating an output so we actually get something out of the whole thing. And now let me show you actually in action. And now what I have here and what I will use for this demo is this device. Yeah, now it's probably a little bit better. This is the onboard computer of a satellite, something that goes into space. I wanted to spice this up for you, and while Hastlayer can be used in the cloud, like in Azure, or it can be used on premises via your own FPGA devices, FPGA cards, this is something more exciting, I think. This is actually the onboard computer of a satellite, and it has two things. It has a little ARM CPU, a 2-core ARM CPU, so much like what you have in your phone. And secondly, it has an FPGA. These two are on the same chip. They work together, and this runs a little Linux, and it runs .NET. So I will now switch over to a shell window that I'm remoting with into this board here, and I'm running a demo application here. And so again, this is some small specialized Linux. It has .NET. It has the completely standard .NET, so we just download it and installed it. And now what happens is that Hastlayer starts, it generates the hardware, and then it starts executing the algorithm. First, it executes it on the CPU, so on that 2-core ARM CPU, and then it executes it 3 times on the FPGA part. So let's see the results. Let me scroll back up. And what we see here, that on the CPU, that parallel algorithm that I've shown you took about 25 seconds, give or take. Now let's see how much it was on the hardware. And here's the result. Well, on the hardware, it took around 240 milliseconds if we are talking about just what happens on the FPGA chip. But that's not always the interesting thing. Rather, you want to know how much it takes from the very beginning to the very end. So pretty much from the beginning of the method call until the end of the method call. And well, that was about 300 milliseconds. This is the big difference here is because of JIT compilation and caches not being warm. But if that's not actually the case, if we do a second execution, then it's still exactly the same on the hardware itself, but now it's roughly 250 milliseconds altogether. So it's 100 times faster. 250 milliseconds versus 25 seconds. Now, again, this is not a real-life example, but still we got a speed up of 100 times. And by the way, the power consumption is even lower than that. We also have all the results, details, measurement methodology, etc., up on GitHub too. So your mileage may vary, but this here shows you what's possible with FPGAs and with Hastlayer. And you may ask that, okay, I've shown you this class here, but surely there's something else. So this is the algorithm, but what's the glue that holds together my normal .NET application and what runs on the FPGA, where the logic that runs on the FPGA I implemented here? Well, the glue is actually also demonstrated here in this demo program. And this is how you interact with Hastlayer. So the code I'm showing you here is pretty much what you would have in your application between the rest of your app and the core logic that you want to accelerate, which, by the way, can be not just a single class with a single method. That was just a simple example. So how you use Hastlayer is that first there's some configuration. That's basically the most important thing here is that we are telling Hastlayer which hardware it will use, because there are a lot of kinds of FPGAs. And secondly, we also tell it that this parallel algorithm is a class that we want to invoke from the host PC. And then comes the actual hardware generation. So that's what we have also seen in the demo. And this method call here is actually what generates the hardware implementation. And I will also show you that, by the way. But this was mostly plumbing and configuration until now. Here is where the actual execution happens. Here is where you run what's now implemented as FPGA hardware. And the remarkable thing here is that there is nothing really remarkable. Really, you just call the same .NET method, the same method from that C# class that you would otherwise call. Now, there's one thing, this line here, that makes the whole thing special. With this generate proxy async call, we take the normal C# class and an instance of that normal C# class and wrap it into a dynamic proxy. This will allow Hastlayer to hijack the method calls and say that, okay, I see we have called the run method. Now I will transfer the whole execution to the FPGA without you noticing anything. So after that, you just use your now hardware executed and hardware accelerated algorithm as usual. Nothing special here, really. And Well, I've shown you how you would utilize Hastlayer, but I didn't yet show you how Hastlayer works under the hood. So let's take a quick look into that. This is the device that I've shown to the camera. This is pretty much like something a bit smaller than a credit card. This is the actual onboard computer that also goes on board of satellites and drones or inside robots. And that chip in the very middle was the most interesting. That's the mentioned ARM CPU plus the FPGA. Also, what I've shown to the camera was a little bit bigger because I've also shown you this board, which is a motherboard for that previous smaller one. This is just for development. This is just for us to be able to plug all things into it, like a power supply, or plug it into a USB port. And now let me show you what Hastlayer actually generates. So I used a lot of really like metaphors here, like we are generating the hardware, but let's see where the rubber indeed meets the road. Let's see some code again. Because what I'm showing you here is code, but it's hardware code. This is the code that Hastlayer generates. This is actually where the magic happens, or where the magic is implemented, rather, because this is pretty much the thing that usually a hardware engineer writes. This is, by the way, written in a language called VHDL, which is, again, kind of language, but it's a hardware description language. It's not a programming language. But if you scroll down a little bit, we can see some familiar things like function and begin and if, things like that. But still, this is hardware code. Sometimes some part of it look like some kind of program from a, if you are looking at it from a distance, but still, this whole thing will be turned into a piece of logic hardware in the end. It's not software. And if you scroll down a little bit, we'll see a lot of unfamiliar things. So you can see that it's actually different, like this block here. These are type declarations in hardware code. But what's more interesting, and why I'm showing you here that I'm showing you this here, is that here's something with the name parallel algorithm. Now, this is the name of our class, right? So something interesting happens here. And that something interesting thing here is, check this out. It has the index 0. And if you scroll down a little bit, we have exactly the same thing, but now with the index 1. And if you scroll down a little bit, now with the index 2. Can you guess where I'm going with this? Well, if you scroll on a little bit more, now we are at the index 239. And if we scroll on a little bit even more, we finally arrive at the same thing, but with the index 259. Now, why is this interesting? Still remember that in Visual Studio, I've shown you that we start 260 tasks here. Now, those 260 tasks are actually indeed turned into kind of 260 little cores on the FPGA. And this is where you see it. Here we have the 260 copies of our algorithm. Well, what I'm showing you here are just the type declarations, so this is not the actual logic. If you scroll down, that's where the whole logic is implemented, but it's a little bit long. This is hundreds of thousands of lines of code, or at least tens of thousands of lines of code. But still, this is where the computing benefits come from. This is why FPGAs can be faster than a CPU. And this is also why it can be so power efficient, because this is not a generic processor that we have created here. This is something that just computes what our parallel algorithm class needs to have computed. This FPGA can do nothing else, just compute what parallel algorithm needs. And because of that, it's super efficient. There's nothing else for it to do, just this. But, well, you need to go low level for that, what Hastlayer did for us here. Now, is there anything else interesting? And there are a couple of things. First of all, we support a platform called Xilinx Vitis. Xilinx is one of the FPGA manufacturer companies out there. And why this is interesting is because Vitis is a little bit like .NET. It's a kind of a platform in itself that you can use to target multiple devices. It's a little bit of an abstraction, which is a big thing when it comes to such super low-level things like hardware development. And because of that, we can support with relative ease many different hardware. For example, high-performance cards that go into data centers. Azure, for example, or AWS, and some other cloud providers have such high-performance data center accelerator cards, and Hastlayer supports them. You can also use similar cards on premises, so it's not just for a cloud. Or you can use smaller cards, smaller FPGAs anywhere else. And you can also target the aerospace industry, as I've shown you with this onboard computer of a satellite. Now, we are actually working on putting this into orbit. So I will keep you updated when .NET goes into space. We have done some benchmarking. Again, the details of these are up on GitHub, so you can read up if you like. What I've shown you with this parallel algorithm on this device is just one data point, one example. As I said, your mileage may vary based on a lot of factors. We have benchmarked a different hardware as well called Alveo. Now, these are the big data center accelerator cards. And we have seen something ranging from a 4 times speed up to a more than 30 times speed up, and 20 to 120 times power efficiency increases. Now, just to be clear, you can't really compare an FPGA with a CPU in a fair way, because these are completely different devices. Really, the question is what's faster for your specific algorithm. Now, what we compared here was a high-end CPU with a high-end FPGA. So this is not like comparing the high-end FPGA with this little ARM CPU here. Both chips were high-end here in the same Azure virtual machine. And similarly, when trying to compare apples with a different kind of apple, at least, when we are benchmarking the Zinc devices, that's what I've shown you. That's the onboard computer. And we have actually seen here much even better numbers. But again, these two devices are not comparable. We are comparing, in this case, a low-end CPU with a low-end FPGA. But they are also low-power ones, so that's why they put them on board of satellites. Also, an interesting thing is that with Hastlayer, you can have your own number formats. And now, if you are working a little bit in the machine learning space, you have probably heard of reduced precision floating point. The point there being, pun intended, the point there being that you trade some accuracy of the numerical results for speed. And how you do that is that you use smaller floating point numbers, smaller number formats to store fractions of numbers. Now, when you are an ordinary .NET developer, you usually use doubles or floats, the double and floats type in .NET. Perhaps if you are working with money, then decimal, but basically that's about it. when we are going into machine learning and more specialized areas, even with .NET, then it becomes interesting that you use different number types. Even rolling your own number type that's somehow optimized for your use case. And this is what happens with the number type called Posit as well. And now, Posit is not invented by us. It was created by a mathematician called Dr. John Gustafson, who has been working on it for the last couple of years in Singapore. And Posit is a generally useful number format that's a drop-in replacement to something like the doubles in .NET. But it aims to be better. So it provides more accurate answers, more accurate numbers with the same amount of bits. Or to put it otherwise, you can use fewer bits for the same kind of accuracy, which translates to speed and storage benefits. What we have done here is that we have implemented a Posit struct pretty much in .NET that you can use from a .NET library to have Posit numbers in your .NET app. But at the same time, we have done it in a Hastlayer compatible way. So now you can also turn it into a piece of logic hardware. So we could say that with the push of a button, you pretty much get a Posit processor. So you invent your number type and you can get a processor for it within seconds. Now, how cool is that? We have some plans for the foreseeable future. We would like to have more use cases. So if you have use cases for such kind of hardware acceleration, please let me know. I would be very happy to see whether I can help. We also partnered with the Wigner Research Center for Physics to see how scientific computations can benefit from Hastlayer. And FPGAs are really becoming commonplace. Really, in all the major cloud providers, you can run them by the hour. And the CPU manufacturers also know this, because Intel brought the then second largest FPGA manufacturer called Altera. And AMD more recently brought the largest FPGA manufacturer called Xilinx. So, you know, we are pretty much nearing the end of Moore's law, because we are reaching physical limits. So simply putting more stuff onto a chip doesn't cut it, because it can be smaller. So something else needs to happen. And one of the ways out to still keep computations faster is making the architecture better. One of the ways to do that is combining a CPU with an FPGA, because that way you can have kind of a core in your CPU or part of your CPU that can be reconfigured. So it doesn't need to be generic. It doesn't need to be able to run any code. It just needs to run one code, but very fast. And with FPGAs, that one code can be changed because, well, it's reconfigurable. So to wrap this up, if you like this, and I really hope you did, then please check out the SDK. As mentioned, everything related to Hastlayer, everything from Hastlayer itself, and all the samples, all the measurements, everything is up on GitHub. And be ready, because I think FPGAs are coming. Now, if you perhaps remember how it started with GPUs, using GPUs for computations other than just graphics, roughly 10 years ago, I think it's something similar. We are probably where GPUs were maybe 6-7 years ago. So they are generally available. The hardware is not special. Working with FPGAs is not something too special nowadays, but you need a tool like Hastlayer to really make it easy. Well, easy for us software developers, at least. So thank you very much. feel free to reach me if you have any further questions, or just go to GitHub, of course. And now I think we have a bit of time left for a Q&A if people are interested.
Yeah, does anybody want to, if people want to post questions into the chat or just mute yourself and ask, feel free. I've got one, and that's what's the limitations of this compared to like just writing for a CPU? I'm guessing the memory footprint, well, the footprint of like kind of the operations. What is this stuff in like if you write in C# which can't get compiled?
A great question, and yes, there are limitations. There are limitations in two ways. First of all, not everything makes sense on an FPGA. So, for example, you can't write to the console because there's no console. Secondly, we haven't implemented all the .NET features yet. We are actually indeed talking about .NET still. For example, a lot of bells and whistles that C# has, those are actually C# features. And the C# compiler takes that very nice C# code and creates something a lot simpler with a lot fewer features, the intermediate language representation in the DLL files. And that's what we process. And because of that, we support a lot of features without explicitly supporting them. But still, there are a lot of things lacking. That's documented. So if you check out the docs on GitHub, you will see an exhaustive list of what's supported explicitly. So, well, everything that's not there is unsupported. Secondly, if you just try it out, you write some code, you tell Hastlayer to process it, you will get an exception if something is not supported.
There's a few questions in the chat. I can read them out to you if you want. Somebody says, does this stack use the built-in .NET garbage collector?
The short answer is no. The long answer is that it's not necessary, or it's a different approach altogether. Pretty much on the hardware, why it can be, or one of the reasons why it can be so efficient is because really everything is hardwired there. Under Windows or Linux, we have virtualized memory. While there's physical memory, we as software developers don't really care about that. Even if you go low level with C++ outside of .NET, you are not dealing with the physical memory directly. You are dealing with virtualized memory. You ask the operating system to give you some memory, and the operating system will decide where that actually is. And it will also decide whether that piece of memory you got is currently actually in the physical memory or it's swapped out, etc. Now, on the hardware, there's no virtualized memory. There's physical memory, and that's it. Actually, the board itself has some RAM on its own. So what you can do from Hastlayer is that you can use that RAM as kind of a fixed-sized array. When you, in the beginning, tell Hastlayer that you need this much memory for your algorithm altogether, then you have that memory and you can do whatever you want in that memory. There's no need for garbage collection because there are no other software running, so it's not a competition for memory, and it's a fixed physical memory that you are interacting with, and it's just your algorithm that does that. So you have the physical memory space for to yourself until your algorithm runs there.
Cool, thanks. There's another one about debugging. Is it tough?
Sorry, one more note for the previous question.
Yep.
There are also a lot of conceptual and fundamental differences between the two models here. And the other, to make it a bit clearer why we don't need memory management or garbage collection, is because when you say new in the code, then we are not actually allocating memory for an object. We are wiring buses or little pieces of memory into the hardware that will represent the data that object contains. So we even in that looking at that way, we don't actually need memory management, since for almost everything we are not using memory. We are using the hardware fabric, so to say, on the FPGA. And debugging, yes, it's hard, but the good news is that you don't have to do that, because the idea here is that you do all your debugging in .NET as usual. When it would be necessary to debug on the hardware, this would be the case when Hastlayer has a bug. That's not out of the question, and we did see it happening, that the computation on the hardware was different than what it should have been, although we don't know of any such bugs. But the point here is that you, as a user of Hastlayer, you only need to debug in .NET. Now, there is actually debugging on the hardware too, but that goes into the territory of hardware development. And yeah, how you do that is with some hardware engineering toolbox. You pretty much see the waveforms of signals going into specific wires. So it's the debugging is pretty low level as well. But if you have such an issue, if you notice such a bug with Hastlayer, please open an issue on GitHub and we will debug it for you.
Cool. There's another question about what real-world applications is he using Hastlayer?
We had quite a lot of interest from finance. So I mentioned automatic trading on the stock market. That's actually one of the prime examples of FPGAs being used for accelerated computations, and it seems that Hastlayer is suitable for that as well. Otherwise, we are currently looking into accelerating image processing, specifically image processing in the space industry. So when there's a satellite that observes the Earth, then usually it captures data that's in some way an image. It can be an optical image, so like a picture, or it can be a radar image, which is what's important there is that it's still a two-dimensional array of data that we can process with image processing algorithms. We don't have any results on that front. Well, we have some bad first steps, but we don't have any end results. That's still an ongoing thing.
Cool. The next one is there a way to generate VHDLs, test benchmarks?
Sorry, generate VHDL what?
Test benches?
Test benches.
Yeah.
Yes, actually, and that's also an area of hardware engineering. So hardware engineers do that, but this is just as debugging, as I mentioned. That's not something that you usually need to do when you are working with Hastlayer. Of course, if you are interested, you can do that. And FPGA developers do that a lot because actually the first step in debugging a hardware design is not to execute it on an FPGA, but even before that, to simulate it as hardware. So there are hardware simulators that you can use to look into what the signals do on the chip without actually using a chip for it. It's quite a fascinating thing, very hardcore, very low level, but yeah, hardware engineers do that. We also have FPGA developers who work on Hastlayer, work on the FPGA parts of Hastlayer, so you don't have to. And sometimes they do such kind of debugging with with so-called indeed test benches.
Cool. I think I've got one more question, which is, does apps run directly on the hardware instead of running on the OS, on an OS, I think.
Sorry, what was the first part of the question? I couldn't write.
Does apps, I'm guessing, does the software run directly on the hardware instead of running on the operating system?
Sorry, I still didn't get the first few words. Let me check out the chat.
Yeah, I think you've covered this.
Oh, okay. Oh, yeah. And the answer is yes. So it actually runs on the hardware, or runs as the hardware, rather. What I'm showing you during the demo showcased that. So in that case, indeed, the FPGA was doing the work, and it's so removed from even the concept of an operating system that it can be actually used alone. So how we aim to or what we aim to support more is that is the use case that, well, you have a slow algorithm, you want to make it faster, and the application still runs on a standard PC, a server or an embedded one, but still a PC architecture, and you offload some computations to the FPGA. But you can also use an FPGA alone, and in some of the financial use cases, that's actually what's happening. There's no PC at all. You take the FPGA, you pretty much put it onto a network interface card, and it talks directly on the network. So that's also possible. Hastlayer kind of supports that, but we don't explicitly make it easy because that wasn't the goal. But you can take a hardware design that Hastlayer generates and plug it into any other hardware design.
Cool. I think that's all the questions.
All right, great. Thank you very much. Great questions.